we are going to go over the rest of the answers for S10I exponential growth and decay. As I've mentioned before, all of these problems are very similar, and the main important formula is that we've got y equals k times a to the power of x plus c. Okay, where c is our horizontal asymptote, and k is represents if it's how stretched it is, and a, if it's greater than 1, it's growth, and if it's less, if it's between 0 and 1, it's decay. All right, so let's go where we start off where we left off. The last problem we worked on was number 2, so let's talk about number 3. So we've got this initial equation. So notice it's to the negative x power. So I need to take the reciprocal of this a value, so 1 over 1.45. So 1 over 1.45 is going to give us a value of a that's less than 1, so it's decay. Our k value is 70, our a value is 1 over 1.45, and our c value is 21. So with this information, the initial temperature is the 70 plus 21, and you can get that value by plugging in 0 to figure out the initial temperature. Anything to the 0 is 1, so 70 plus 21 is going to give me our 91 degrees. Question C, find the temperature after 5 minutes. So we take our equation, we simply plug in 5 in for x, and then we get 31.9 degrees Celsius. Question D, sketch. We want to find the number of minutes it takes for the hot chocolate to reach 50. So just like in our previous equations, our previous problems, you type in 70 times 1.45 to the power of negative x plus 21, and looking at our scale on our graph, we know our we do window, our y max is going to be 100, our x max is going to be 12. We can hit graph, and we're going to see our curve looking like this. Okay, and we want to find the number of minutes for the chocolate to reach 50 degrees. So I needed to draw a line here at 50 also. Okay, and that's what I've drawn right here. So so the number of minutes it takes for the hot chocolate to reach 50, we need to figure out the intersection. So second trace, 5 for intersect. First curve, I hit enter. Second curve, it's the other equation, I hit enter. It says guess, I hit enter, and my intersection is 2.37. Okay, our horizontal asymptote is the c value, which is 21. So remember to write your horizontal asymptote as y equals 21. Don't just write asymptote equals 21. My room temperature is the c value, which is 21 degrees Celsius. Okay, next. Okay, this one was a little bit tricky. Let's talk about this one here. So in 1998, 200 bears were introduced to the island off of Alaska. The population exponentially grew. So B sub 0 is our initial population, which is 200 bears. In year 2000, the population was 242. Find the A value. So basically what I did is I plugged in 242 in place of B sub t, and this is 2 years later than 1998, so I'm going to put a square in for A. So we divide both sides by 200, And so then I get a squared is equal to 242 divided by 200, which is 1.21. And I take the square root, and I get a is 1.1. Okay, this is growth, right? And it's 100% plus 10%, so we know that the bear population is growing at 10%. So now I've got my new equation. 200 is my initial population. My growth rate is 1.1. And so for question C, they want to find the expected bear population at 2018. So 2018 is 20 years after 2019. So my x value, I'm going to plug in 20. And so after I've plugged in 20 as the power of x, we get 1,345 bears. Okay. Question D, find the expected percent increase in population from 2008 to 2018. And so at 2018, the population is 519. So if I do this population minus my 2018 population divided by the 519, we're going to get it's an increase of 159%. How long will it take for the population to reach 2,000? So just like the other examples, I'm going to type in y equals 2,000. And the other equation in my calculator is y equals 200 times 1.1 to the power of x. And just like the other examples, you hit second trace and then 5 for intersect. And then we find out the intersection is 24.2. All right, let's do problem number 2 now. Okay. How much radioactive substance was there initially? 250 grams. Okay, for these, I plug in 400 in for the power, 800 in for the power, 1200 in for the power, and I get these answers. They want you to draw a sketch. So I typed in this equation. And okay, so in order to get points to draw my sketch, this is important. You should write this down on your paper. To see the table, I'm going to press second window and change the delta TBL to 0 and the delta TBL to 200. Let's do this together, because I think this was a little bit tricky. Okay, so what is my equation? My equation is, I hit y equals. My equation is y equals 250 times 0.998 to the power of x. Okay? And in order to see the graph, I need to press window, and I'm going to change the x max to 1400. I'm going to change the y max to 300, looking at the x max and y max on my graph. And then I get this graph. Now if I simply press second graph, my table isn't it would be impossible to get all the way up to 1200 by just pressing down arrow. It would be impossible. So what did we do? You press second window to change the delta TBL start. So we're going to start at 0, and then the delta TBL I'm going to set for 200. And the reason I do that is I want to get these points at 200, 400, 600, 800, and so on. So by changing this to delta TBL to 200, if I do second graph to get a table, now you can see that the table goes up by multiples of 200. Okay, and then I can take these points here and plot them on my graph to get a graph. Okay, and then to get this intersection here, just like in the other examples, to find how long it takes to decay to 125, grams, I'm going to type in 125, and then just like in the previous example, we find the intersection by second trace, 5 for intersect, enter, 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 and we get that it's 346 years. Okay. Question number 5. Find the percentage increase. So we take our predicted population minus the initial population divided by the initial population, and then we're going to get 10% increase. We're going to talk more about this percentage increase when we do the financial math chapter. Okay, given the percentage increase remains constant, find the number of kangaroos in the year 2020. Okay, so here's my formula for finding exponential growth. We know it's increasing by 10%, so the A value is going to be 1.10 because it's a growth. It's increasing, so this has to be greater than 1, and it's increasing by 10%. Okay, 2020 is 3 years after 2017, so my power here is going to be 3. So my K value is the initial value, which is 50 million. And so we put that into my calculator, and then we get this value. So the kangaroos double, determine when the kangaroos double. So we want that to be at 100 million. To make this easier on my graph, I'm just setting y2 to be 100, y1 to be 50, and then times 1.1 to the power of x. Okay, so if we're going to do it this way, we change the window x max to 20, y max to 150, and then I get a graph like this. And just like all the other examples, second trace and 5 for intersection. Okay. Example 15. Okay, find the initial weight of the radioactive substance, which is 1,000 grams. Okay. Then find the half-life of the substance. So half of 1,000 is 500. So looking at my table here, my y max needs to be 1,200. My x max needs to be 100. Because of these values, 20, 40, 60, 80, I'm going to change my delta TBL to 20, so I can go up in multiples of 20 on my table. And then once again, second trace, intersect, and we find out these two graphs intersect at 32.7 years. Okay, next. Last page. Okay, the medication is taken by a patient and slowly used by the body, and it has this equation. Find the initial dosage of the drug. It's 120 milligrams. Okay, find the half-life of the drug. So we can type in this equation, and half of 120 is going to be 60. So we can change our window. Our y max has to be 130, which is higher than 120. And then x max, I just made it 20 to see what would happen. And then I got a graph that looked like this. And then if I do second trace and then intersect, we end up that the intersection is 6.58 hours. Find the time when there is only 25 milligrams of the drug left in the body. So I just found the and we found 14.9 hours. Okay, we did the same process. I had a line over here at 25. Okay, and then so I changed. So I had, instead of y2 being 60, I had y2 being 25. And we got this value here. Okay, last question. The value of the cars after t years, I had this formula. Um, State the value of c in this formula. So you can look at the graph and you can see that we have a horizontal asymptote at 1,000. So I know that c is going to be 1,000, and uh, and what does that represent? So this represents that the car is never going to be worth less than 1,000. Okay. Question B, find the value of k. Okay, so we've got a point right here on our graph, 3 comma 8889. So the value is 8,889 equals k times 0.7 to the 3 plus 1,000. So if I subtract 1,000 on both sides, I get this value. And then if I 0.7 to the power of 3 is going to give me this decimal. Divide by the decimal, and then we get k is equal to 23,000. So the initial value is always k plus c. So 23,000 plus 1,000, which is our c value. Our initial value is 24,000. Okay. Question D, how long will it take for the value to be 5,000? So I can hit y equals into my calculator, type in the first equation, type in the second equation. I need to change the window. The y max, I made it up to 12, and the x max, I made it up to 12, and the y max, I made it up to 30,000 because that's what the graph had. And then just like before, I do second trace and 5 for intersect, and we get this value here. Is the car depreciating the same percentage each year? And the answer is no, because it's a lower percent each year because it's worth less than the previous year. Okay, that is it.